So firstly, we import some common packages. And we can create a set with all results at first. So actually, we were using the we just created a conversion data set. We call it conversion equals to 0 multiplied by 45945. So this means we actually create a list of conversion with this much zeros, and then the 0 means no purchase. And then we will extend a lot of ones, okay? And 1 means purchase. So this is this much purchase, which is 200 plus 182. So when this works, the conversion is actually a data list with this much zeros and then this much ones. So literally we just combine all the instances together without have difference of price A and price B. So the reason we did this test is to randomly separated the whole conversion into 2 different groups and then check about the conversion rate difference to see what is the distribution of this conversion rate difference. So we just created this conversion list and then we will put it as the series, because series is more convenient. It is a more structured and efficient data type for data analysis in Python. Series. So then we can check the converse. So this is what the converse looks like. And then the next thing is we will apply this test, but let's show you how we separated this conversion dataset randomly into the 2 different groups without thinking about the price A or price B, right? So we can use the index. We can randomly set up the index. So if you see the table right here, this is actually the value. 0 is no purchase, 1 is purchase. Okay, and then this part, like before, on left side, this called index. So this is the index of each record. So what we can do is we can create a random data set of the index in a range from 0 to amount of our dataset, amount of our records, to pick up the random amount of the dataset. So for example, I can create the column called index. Okay, so index A, it is equals to random sample. Okay, range. So the range will be, before I create a range, let me do this. So the range is actually the total amount of the the data set that we have. Okay, so which is this much plus this much. All right, and then we will using what is the amount of the price A. Okay, so this is all right, and then we need to import the random package. Port random. Okay, so this actually means we pick up this much number from this range. Alright, so I can give you a quick example. For example, I will see if I have a range 10. So range 10 is from 0 to 9. Okay, list. See, this is the this is the range 10 is actually 0 to 9. And then if I pick up using the random sample, okay, random sample, and then from range 10, which is from 0 to 9, I'll pick up 3 different numbers randomly. So you can see, like, each time I run it, I get 3 different numbers. Okay, so it's the same thing. This is the amount of the data we have in this data set, and this is the amount of the number we want to pick up, because this actually match the amount of the price of the amount of instance in the price A. Okay, so this is, if we check this one, and then we can see how index A looks like. So these are all index, so which means we will pick up the number that match with index like this. All right, and then we will do same thing. We will create the index B, which is equals to range n. So range this much, that will minus the, so which means we don't want anything inside of this. We don't want any number other than index A, right? So we can using the minus, but the minus only works as the set. So what we will do is we will set the index A at first to make them as a data set. Okay, so data set looks similar, but it can use to the calculation. If you remember in the first class, it's similar to list, but the thing is the set has to be not duplicated. So we're using set, and the set we can do the calculation, okay, or the operation, the calculation. So we can use in the set of the same amount of the range and the minus index A. So it will looks like that. Alright, so we can print the index A, and we can print index B, so you can have a check about it. Yeah, so this is a similar like index B. Okay, they're similar to index A, but they are not. They're not at the. They're not duplicated with each other. There is no common index between index A and index B. And so the next step, what we will do is, since we have randomly pick up the index A and then index B, so next step is we're gonna create it. We're gonna pick up the number from this index and then calculate the mean value of conversion rate, right? So we're using X. We're using the data set we just created, the conversion rate. We're using X log list index B. Okay, and so this one is actually we pick up the values of the index, the B, and randomly based on the index. So you can tell the index is not sequential. Okay, so which means this is a totally this much index, and then we want to calculate the mean of this one. So we can know that this is the mean, so which means the conversion rate of the group of price B is this much. Okay, so about like 8.3%. And then we can also calculate the conversion rate of group of price A, and then that is about like 7.9%. Okay, the reason we use mean is so because 0 means no conversion, 1 means conversion. So if we sum the value up together, so it's 0 plus 0 plus 0 and then plus 1, and then divided by what? Divided by the total instance number, right? Amount of the instance. And that's actually how you calculate the mean. So this is the quick way for us to calculate the conversion rate. And uh, or you can using the amount of the 1 and divide it by the total number. That's also the conversion rate. But yeah, it's the different way to do so. We can using this, and then we can calculate the conversion difference using B conversion rate minus A conversion rate, and then this is 0.09. So this is how we calculated for the first random separation or first random split. However, what we want is we want to do this kind of steps, this kind of process for 1,000 times. So it's better for me to create a function to do so, right? So what I can do is I can create a function. I'll create a function right here called function permutation function. Okay, so I will have 3 parameters, x and a, which is the amount of the dataset, the amount of the records in group A, and amount of records in group B. And then n is the total number, should equals to na plus nb. And then I will create index b, because I will using index b to minus index a. So I calculated minus b at first. So minus b is the set random sample range n and amount of the records in the group B, right? So it's similar to this. So it's automatically created. And when it returns this. It's not conversion dataset. We actually set up our dataset as x, right? So this one should be the x. X index b minus the x log list indexed a, and then we want to round it to 4 decimal. Okay, so and then let's test about it. All right, so we test this and we run it for once. Conversion rate, this is a, this is B. Okay. So we can see. So that means 0.14. That's the difference. All right. So so you can tell that the difference is different. The difference is quite different, right? So because every time we pick up the different amount of the dataset into group A and group B. So what we will do is we will run this function 1,000 times and then save the difference conversion rate, and then created the histogram to show the distribution of this conversion rate difference and to see the distribution of that. And then we will comparing our observation, which is this number. We will see the location of this conversion difference to see if this happened normally or this is not normally happen. Okay, so let's keep working on it. And what we will do is we will create it. So we don't need this anymore, and we just created. We use a random seed to make sure that we're using the same method of the random, and then we will create perm diff, which is we'll run it 1,000 times. We'll run a perm function of conversions for this in range 1,000, not 10,000. And we can show how it looks like. So it's actually running for 1,000 times. We will have a list really soon. Okay, and while waiting, we can start to create the histogram that we learned from the last 2 classes. Yeah, I need to import the packages. Alright, so it's run out. So we have a data set for the conversion rate difference right now, and then we will just build up this histogram to look at this. Okay, and then we'll make an X histogram using the perm difference. We set up the bin as 11 and the width between each one is 0.9, and we will create the observation line, which is 0. This much. Okay, color equals to black, and line width equals to 2. And we will create the text right here at this position as observed difference with VBox, like this is the box line. Then we will set the X label as conversion rate percentage, and Y label as frequency. Oh, this is too big. 0.03. The printer is 3%, so I need to add a percent. Oh, it's too small. It's too small, so I will change it a little bit. So I will make this difference as using 100 to multiply by it, so that we will see a quite large graph. It's gonna be convenient for us to view it because this is too small. Let's make it a little bit bigger. So the percentage we multiply by 100, and here I'm gonna change it back to 0.0368. We're still waiting it to run. Alright, let's run it again. So yes, you will see that this is the line of our observed, right? The observed difference. You can tell the range is about minus 0.2 to 0.2, and our observation is 0.0368. It's at this part, right? So it's actually located in the most frequent bin. So which means this difference is happened normally.
In a permutation test, we estimate the p-value by checking how often the resample difference are equal to or larger than the observed difference. Inside the square brackets, we have what is called a list comprehension. You can think of it as a for loop written in a single line. It goes through each value named div in the list perm divs. which contains all the simulated difference from the permutation test. For each diff, Python checks whether diff is greater than 0.0368, which is the observed difference from the real data. If that condition is true, it produces a value of true. If it is false, it produces a value of false. So the result of this one-line loop is a list of true and false values, one for each permutation. In Python, true is treated as 1 and false is treated as 0 when calculating an average. The function np.mean then takes the mean of this list. This mean is simply the proportion of permutations where the simulated difference is greater than the observed difference. That proportion is the p-value, which tells us how often random chance alone produces a result at least as extreme as what we observed. Let's wrap everything up by walking through a complete hypothesis test step by step. First, we clearly state our hypothesis. The null hypothesis says there is no difference between the conversion rates of the two pricing plans. The alternative hypothesis says there is a statistically significant difference between the conversion rates. At this stage, we are not trying to prove anything yet. We are just defining what no effect looks like and what an effect would mean in this context. Next, we define the exact question we want to answer. We ask, if the null hypothesis is true, meaning there really is no difference between the two price plans, what is the probability of observing a conversion rate difference larger than 0.0368%? That probability is what we call the p-value. After running the permutation test, we obtain a p-value of 0.332. In plain language, this means that if there truly is no difference between the pricing plans, we would see a difference this large or larger about 33% of the time, just due to random chance. Now we make a decision using a predefined significance level. If we set alpha to 0.05 or 5%, we compare it to our p-value. Since the p-value of 0.332 is much larger than 0.05, we fail to reject the null hypothesis. The final conclusion is that the observed difference in conversion rates is not statistically significant. The p-value tells us that we do not have enough statistical evidence to claim a real difference between the two pricing plans. The small observed difference of 0.0368% is very likely explained by random variation rather than a true effect of pricing.
And now, since we learn how to calculate the p-value using the ANOVA chi-square test or the t-test to calculate the p-value and then the statistical significance of the relationship between the different data types. So now actually what we can do is we can finish the data understanding we did from the section 2. So let's review what we did in section 2. So this is the report from the section 2 practice, right? So we actually did collection, description, quantity, and then exploration. And when we do the exploration, we are trying to find out the relationship between different kinds of data types, including quantitative, category versus category, or category versus quantitative. So the quantitative ones, we don't need to do the further steps because the correlation coefficients is already enough for us to find out the relationship with the significant. And so what we will do is we will calculate the categories versus the categories and categories with the quantity, because we find out the relationship of this kind of data type by observing using data visualization or check about the crosstab, right? So we didn't do any further statistic test on those relationships. So because we haven't learned those tests yet, and now since we learned it, so we can do it. For example, for the categories versus categories, we can using chi-square to find out, right? Find out the p-value. That's all the coding is including here. So now we can finish this. we have, for example, from the section 2 data type, section 2 report, we have all of these categories versus category relationship, and we have the sum up table, right? So now we can do the chi-square between, we can do the chi-square test on this pairs of the categories data to find out the p-value, right? So these yes means we assume, or we feel like there might be a relationship between those kind of data. So now we can actually do the chi-square test on this data. All right. So for example, we will including the table at first, the data. We include the second practice CSV file into this collect, and then this is the data we have. And we will create the function of the chi-square. Okay. So before we did this chi-square function that we learned from here, the 5.3.2, we need a pivot table, correct? That's how we're gonna do. So we will create the pivot table using the columns, different columns. These are the category columns. So we have two different columns that we used to create the crosstab. And here I use the crosstab from the section 2, the crosstab function from the section 2. I think this part when we created the yeah, right here. We're using the function here to find out and created a crosstab, right? So the reason we're using crosstab, but we didn't using the pivot in that we used in this in here. We're using crosstab, but we're using pivot here in section 4. We're using the crosstab function in section 2. So there's kind of different. So you can tell from here that when we're using the pivot, it actually means we use the pivot when there are aggregate data already. So you can check here, we have the headline, click, and the rate. So we're actually just changing this data from this format to this format, correct? We don't need to do any aggregation. So pivot didn't provide any aggregation functions. However, this is the data we have in second practice CSV files. There's no aggregation yet. So we were using a crosstab that provided aggregation functions. That's the reason we're using the crosstab here to create a pivot table for the two different columns. And then we're using the chi-square function from statistic to find out a chi-square value and p-value. And we only need the p-value in this case. So that's the reason in this function we return the p-value. All right. And then we copy paste the category variables from the section 2 reports. And then using the same nested loop method to find out the relationship between the different categorical data. Okay, so this is the variable 1, this is variable 2, and then if variable 1 doesn't equal to variable 2, then we're using the function we created before to test the p-value of these two different data. And then we will only find out if the p-value is less than 0.05. Okay, if the p-value is more than 0.05, then we will not count it anymore, which means there's no relationship, right? And then when p-value is less than 0.05, and then that means there's a statistical significant relationship. So we'll only record those relationships. And then we can find a result that sex and diagnosis has relationship, diagnosis and log, diagnosis and status, log and steroids and status. So these are the relationships with the significant statistical significance. And after we have this result, we can actually update the report like this. So this will be the updating report. We change those relationships we change those relationships when the p-value is more than 0.05, and then we keep those relationships when their p-value is less than 0.05, and then we recorded those p-values in this table.
Now I can using the ANOVA test to test the p-value between the relationship of categorical data and the quantitative data. So we're using ANOVA because the t-test is only works for right here. Right here, the t-text is only works for the binary categorical data like this. So that page A and page B. So right, that's the binary ones. But most of our categorical data are multiple groups. So that's the why we can strictly using the ANOVA instead of t-text to do all the p-value, find out all the p-value. So right here, as we did before, we can create a function called ANOVA test. So the first thing I want you to notice that I created a pair for the continuous data and the categorical data, the quantitative data and the categorical data. So this is actually works as here. See like how we created a ANOVA model like we did before. So you have to be careful about the quantitative data at first and then the categorical data on the right side. And we were using this to create this pair, and so that it will showing something like this, okay? And then in the model creation, and then this is the continuous data, quantitative data to create the pair on left, categorical data to create the pair on the right, and then we can using this pair in this model to generate a ANOVA model, and we can find out the ANOVA table. And so this line is to show the p-value for the ANOVA test. And so we only return a p-value. And then this quantitative variable is what we got from the section 2, right? And then we can using all the quantitative data, we created a nested for loop to do the ANOVA model between the quantitative data and the categorical data. So this gonna show the result of the p-value, all right, using this function. And then we only select the p-value that's less than 0.05. So it's going to return the result only for those relationships with the p-value less than 0.05, which is the significant relationship. And then we can print this result out. So we find out, like before, by checking the relationship, we can find, okay, we have a lot of pairs that might have the relationship like this, okay? But after the p-value, we find out there are only 5 pairs has the significant relationships. So we can update the our relationship table of categorical data and continuous data, and like this. Okay, so we're gonna upgrade the ones with the p-value, the significant ones with the p-value. So we can find out that the status has the significant relationship with literally all of the continuous data. Okay, so now we don't need these rows anymore, so we can actually delete this row and delete this row. And we don't need this. We can delete these ones. So now we only have the 5 pairs that has the relationship with that has the statistic relationship. Okay, so this is how we upgrade the report.